All right. Good afternoon, everybody. Next, we have the first talk for the afternoon session. Our speaker is Masha Baryakhtar. Masha is from the University of Washington, and she is awardee of the Frontiers of Science Award. And in her talk, she'll talk about the detection of ultralight particles with black holes and gravitational waves. Masha, please.
Thank you. Thank you, everybody. Thank you so much for having me here. I've been having a really wonderful time. And today I'll tell you about work from the FSA award, and also a bit of, at the end, I'll say a few words about more recent developments in a similar area. To start, we've been hearing a wide range of really exciting talks in different fields, so I want to situate us in the context. I'm a particle physicist, and I think about physics beyond the standard model, where the standard model is what we've established over the past half century or so, a minimal set of particles and interactions that accurately describes our universe at the smallest level. Some examples of how successful it is include the Higgs boson discovery over 10 years ago now, as well as the continuing success of higher and higher precision measurements where we can predict observables to a ridiculous number of decimal places that agrees well with the theory. So, of course, many of us are here because I think this is not the end of the story. And there's many open questions that are left. In the last few weeks, we've been hearing about ideas to address many of the big questions, like why is the Higgs boson so light? Why is the cosmological constant so small? What happens to gravity at the highest scales and at the highest densities? And questions about, the earliest times in our universe. Since this is a large international audience, I also wanted to put in a shameless plug for the University of Washington, because we're a very young group. Not all of you might know that we have these great faculty in our high energy theory group, most of which have started there in the last 3 years. So, keep us in mind if you or your students and postdocs are thinking about exciting places to think about these questions. So for this talk, I'll be focusing on a very specific set of questions, which is how do we look for new ultralight particles? These are motivated by two sets of questions. One is a theoretical puzzle within the standard model, which is called the strong CP problem. Another way to put it is, why is the electric dipole moment of the neutron so small, which new very light particles? And there's experimental observations. We know that there is dark matter all around us, and that points to the presence of also of new light particles. So I'll tell you a little bit of motivation for these particles. For many of you, this will be a review. And then I'll talk about how to look for new ultralight particles using the densest objects in our universe, black holes. And then I'll say what kinds of observables we can expect from combining black holes with new ultralight particles and different types of signatures that we might expect across different spectra. So why are we really excited to look for this particle called the QCD axion? It starts with the strong CP problem, charge and parity, which says that, basically all of what I showed you about the standard model, all of the terms that are allowed by symmetries seem to exist in nature, except for one, which is the term that violates charge and parity in the gluon sector. If it were there, it would give the neutron an electric dipole moment. It's a bit hard to picture CP, so let's just do a parity transformation. Neutron, you can see that if it has both the dipole moment and spin, under a parity transformation, these would transform differently. And so this is not consistent with what we observe. If you do have these experiments that try to measure the presence of a dipole moment, you find that it's very, very small. In particular, if you just take theoretically expected numbers in the standard model, the expected value for the size of the dipole moment is about 10 to the minus 16 in units of e centimeters. But the experimental upper bound is about 10 orders of magnitude smaller now, which tells us that this dimensionless number, which characterizes this one term that seems to have been left out of our standard model Lagrangian, to be less than 1 part in 10 to the 10. So if this is a fixed parameter of the theory, this is a huge unexplained tuning, not as big as the cosmological constant, but it does give very simple and concrete prediction to test, which is a new field called the axion. This was proposed over almost 50 years ago now, in the late 70s. And the idea is basically making this theta parameter a dynamical quantity. So if you have potential that depends on the value of this axion field, which is a function of theta, and then it's like any other field, it wants to minimize its potential energy and relax to zero. So we will take, and this potential is generated exactly by the QCD interactions that I described before. So this is a very simple trick to get rid of the strong CP problem. So then, how do we look for this new particle? Well, before I go there, I also want to mention that from the effective field theory point of view, that's all you need to know. But it turns out it's very nice that the QCD axion and many axion-like particles also appear in theories that try to UV complete standard model and just theories like string theory. These axion-like particles seem to pop up quite often when you have compactifications of dimensional model. And so this is a broader search for a broader class of particles, including the QCD axion, but also a test of these types of ideas at very high scales. So to sum up the introduction, axions are, the solution to this, one of the low energy theoretical puzzles in the standard model. And they're an approximately massless particle that's entirely dictated by properties of QCD and described by one parameter. You can think of it as its mass. They're predicted to be very light. I won't go into this, but they're also excellent dark matter candidates. And as I mentioned, they're motivated by string theoretic constructions. So all of these points describe the QCD axion, which is a really interesting particle to be looking for. But the last 2 points also apply to this broader class of particles, like axion-like particles and also other very light bosons. So it's also interesting to look for this broader class of light states. So let's see how we can look for them with using black holes. So I'll talk about black hole laboratories for ultralight particles. Before that, I want to introduce a cartoon for the process I'll be describing, which is superradiance. It's originally, when you hear about it, it sounds a bit counterintuitive, but it's actually a very basic property, not just of complicated objects like black holes, but as a generic property of any motion within the presence of dissipation. So if we have, for example, a cylinder with a surface that has some friction to it, you have the mechanical problem of calculating what happens to the trajectory of a ball that comes into contact with the cylinder. If the ball scattering it with the cylinder has a relative velocity, the friction at the tangential surface will cause it to slow down and lose energy. However, if the cylinder is rotating and it's rotating very quickly so that the tangential velocity of the cylinder is faster than the velocity of the ball, then the ball will actually extract energy from the rotating object. You can think of it as in the frame of the object. Slowing down the ball actually means giving it a kick and speeding it up in the lab frame due to the relative motion and to the presence of dissipation. So this means that if you have relative motion through, for example, rotation and some dissipative processes, you can extract energy from your system. And this is a kinematic example, but it also happens with waves. For example, if you have a rotating cylinder with some absorption and you send in a light wave or any other kind of wave, the cylinder is rotating quickly relative to the angular velocity of the wave, then you can extract energy from the cylinder by slowing it down. And this was studied by Zildovich and others in the context of different kinds of waves. And he realized that the same process will happen for a black hole, which is, in a sense, the perfect dissipator. It absorbs everything that enters the black hole horizon. And so it's one of the most efficient ways to superradiate is to interact with a rotating black hole. The condition for when this occurs is when, again, the phase velocity of the incoming wave is less than the angular velocity of the rotator, or alternatively, the energy over the quantum number is smaller than the black hole angular velocity. So this was, at the time, this was very controversial. People thought that Zildovich didn't know what he was talking about because he didn't do the full black hole calculations, but eventually it was realized that indeed, in this case, as in many others, black holes behave just as regular objects and have the same properties in terms of emission and absorption of radiation through superradiance. So this happens presumably all the time when, for example, gravitational waves come in and interact with a rotating black hole. Here you can see in blue color-coded incoming gravitational wave with some angular momentum. It gets re-radiated with a much larger amplitude. So this is a full numerical GR evolution by Will East. And you get a lot of energy out of the black hole rotation, which then gets transferred to the radiation, which goes off to infinity. But this is a one-time process, and typically we would not really hope to observe it unless the initial radiation state was already very large. However, it's been known for a long time that waves trapped near the black hole, either through some artificial boundary or a process like a mass term, which creates a gravitational trapping potential, will repeat this superradiating process continuously. So if you have a very small mass, mu, that's of the order of the black hole size, you can have bound states in the vicinity of the black hole. And any rotating black hole is classically unstable to the emission of these, to the generation of these bound states through superradiance. And it was realized in around 2010 that astrophysical black holes have exactly the right size to be able to do this process for particles that are actually interesting in terms of beyond the standard model physics, because you want the wavelength, Compton wavelength of the particle to be roughly comparable to the black hole size. So that corresponds to, for solar mass black holes, kilometer wavelengths, or masses around 10 to the minus 11 electron volts, which is much lighter than any particle that we know of today, but is interesting for particles like the ones I described, including the QCD axion. So these bound states are very simple to leading order. They are just like what you would do in quantum mechanics class when you solve for the bound states of hydrogen. They're characterized by their three quantum numbers, the principal and angular quantum numbers, NL and M, and as well as by the binding energy, which is the product of the gravitational strength, G Newton, the black hole mass, and the particle mass. So far away from the black hole, you just have a 1/a potential, and this is exact. Of course, close to the black hole, things are very different, and because of the absorption on the horizon, you can calculate that the energies of the particle states aren't just the hydrogenic energies, which are the mass and the fine structure constant, which I've defined to be an analogy to the regular fine structure constant in ENM. But there's also an imaginary piece, which is exactly the superradiance process. And this imaginary piece can be positive or negative depending on whether the superradiance condition is satisfied. So for particles in the right mass range and for rapidly spinning black holes, you will extract energy from the black hole into a growing set of these bound states. So we can do an example. Let's look at a figure in the black hole mass and black hole spin plane. The blue regions here indicate where superradiance, the sign of superradiance is positive. And the states are growing, and they're growing within a reasonable astrophysical timescale. So for states with angular momentum 1, 2, and 3, if the black hole is born anywhere in the blue region here, it will superradiate and spin down. And on the right-hand side, I'm showing the number of particles that you expect in this bound state. So as a function of time after the birth of the black hole, the number of particles grows exponentially, and it saturates once the black hole finds itself on these lines, which are the superradiance condition when the angular momentum, the angular velocity of the black hole is equal to the angular velocity of the particles in the bound state. And as the number of particles grows, it will saturate and eventually decay away. So this is very exciting because black holes have a lot of energy to give up. So even a small fraction of their energy creates very dense bound states. So the bound state, again, grows by extracting angular momentum and energy from the black hole. And you end up with a few percent, up to a few percent of the black hole mass distributed over tens of black hole radii. So now you have the system where you have a black hole, and then you have some density, large density of particles that can be equivalent to the density in neutron stars, but made up completely made up of some new ultralight particles like the QCD axion. So if you have a very large density of particles and you have some time dependence, then you can radiate into gravitational waves without assuming anything else about the interactions of the particles. So in the particle picture, you can think of this as two axions annihilating two gravitons, or in the classical picture, which is perfectly fine, you can think of this similarly to what we heard yesterday in Maria Alessandra's talk about rotating neutron stars. This is a very dense rotating object that's not perfectly axisymmetric, and it will radiate coherent monochromatic gravitational waves. So this is great because we are already doing searches for such continuous monochromatic gravitational waves. And so we can hope to see signals of these clouds that emit gravitational wave radiation in current gravitational wave data. Yes? It's not axisymmetric because it has a it's a non-trivial angular momentum states, and I'm also assuming that these are real fields. So the overall energy density has a component. It has a dominant component that's axisymmetric, but it has a subdominant component that's proportional to the angular velocity of the particles. So it basically looks like a dumbbell that's rotating, like an L orbital. Yes. I mean, you can also have a complex field, which if you think of the complex field as having two real fields, if they don't grow at exactly the same time, which is very unlikely, it will also not be perfectly axisymmetric, but you can tune it to be exactly axisymmetric in that case. The real one cannot be axisymmetric. Yes. Good. Yes, and please ask questions during the talk. It's rather than waiting till the end. That way we all stay on the same page. Okay, so this is to say that this slide is just to say that lots of people are excited about this, which is great. So there are these searches for gravitational waves that have been carried out both within and outside of the LIGO and Virgo collaborations, and there's different ideas of how you can look for these types of signals. I'll just mention a couple in the interest of time, which I think are interesting. So this plot you might have already seen yesterday at the Continuous Waves talk, where led by Sylvia Zhu with Maria Alessandro, we looked at how many detectable signals you would expect in LIGO data today if a particle of this mass, like the axion, would exist in this mass range of order 10 to the minus 12 electron volts. So on the y-axis is the number of detectable signals, and I'm showing several different assumptions about black hole distributions. So here we're looking for long, weak signals that come from throughout the Milky Way galaxy, where many black holes have been born over the course of cosmic time. And each of those, if they have the right mass and spin, could have grown a cloud of these particles around it. In that case, some of the signals will still be around today because they're fairly weak and they continue for a very long time. And so they can last for about 1 million years. If you believe that the spin distributions of black holes in our Milky Way are roughly evenly distributed from 0 to 1, where 1 is extremal, then you would already exclude many of these particles because you would have expected to detect hundreds to thousands of these signals. Maybe that's too optimistic, and for smaller spin distributions, you still need to take more data and do more analysis to really, oops, what happened? Nothing happened, okay, to see these signals. So I think these searches are really exciting and could potentially see something in the next few years, but they are also sensitive to our assumptions about the masses and spin distributions of black holes in our galaxy, which we have no way of experimentally verifying. There are many models that give different predictions, but of course it's good to be really sure if you want to convert it to particle parameter space. So these are searches that are being done today. Future searches could also potentially tell you, so what you need is a rotating black hole, and you need to know where it is, what its mass is, and what its spin is. You don't really need to know where it is, but that makes your searches a bit more optimal. So if you have an axion, which is a spin 0 particle, or a dark photon with a mass, which is spin 1 particle, with current sensitivities at LIGO, you probably don't expect to see these signals. These black hole mergers are just happening too far away, and these gravitational wave signals are too long. But with future observatories that are currently being discussed, potentially you could see tens to hundreds of signals, post-merger signals, and for a dark photon spin 1 particle, you could potentially even already start seeing these signals in the 04 data, which was some work that was done by these guys down here. So stay tuned. Maybe, in the next LIGO Virgo data, you will start seeing some signals in these follow-ups as first evidence of massive dark photons around black holes. Yes. Yes. So for the excuse me, the gravitational wave power scales very sensitively on the ratio of the boson wavelength to the black hole size. So if alpha is this constant that I described, which you can also think of as the ratio of the black hole size over the wavelength, then the gravitational wave power scales as something like alpha to the 14 plus 4L, where L is the angular momentum number. The reason for this is that the particles are non-relativistic or semi-relativistic in these clouds, and the gravitational waves that are emitted are, of course, relativistic. And so there's a lot of, basically, you're averaging over a large source with a very high frequency wave that you're trying to emit, and that power gets reduced. Alpha is also, you can think of as the typical velocity of the particles in the cloud, so it characterizes how far away you are from being relativistic. So that is to say that the 1,000 years number is for some alpha, but of course you can get a large range. So it can be a few hours, or it can be basically a billion years. So the signals that we're looking for today in these blind searches are lasting millions of years to billions of years, because probably there isn't a black hole. Well, we're pretty sure the black hole that was born 100 years ago, we probably would have seen, some records of it being created. And there's many more old black holes. But for these signals, you're looking for very high alpha, very dense clouds that emit very bright signals. And those we can see from further away, but they last for a shorter amount of time. Yeah. Yep. Okay. So that's the gravitational wave signal story. And as I mentioned, there's a lot of really exciting work happening here. And I think, doing these searches is really important and could lead to a discovery. In the last part of my talk, I want to tell you about two other directions that one can take with this story, which is that, of course, originally we started talking about this by thinking about new particles. And so we want to understand how doing these searches relates to the particle physics parameter space, and how these conclusions about gravitational waves, for example, depend on the underlying theory that we're exploring. Interest of time, I'll just give you a summary, but please do ask questions if you're interested. So first, I'll talk very briefly about axion self-interactions. So this is the axion parameter space that I showed before. So we have the mass and the UV scale where the axion is generated, and the QCD axion is the line in this parameter space. So this is not depending on any kind of interaction with a standard model. This is just from the fact that the axion has a potential generated by QCD. And then, of course, the axion will, in addition to a mass, also have higher order interactions, because it has a periodic potential that's approximately a cosine. So we've been looking basically down here, where the interaction scale that suppresses the axions is of order to the Planck scale, which is reasonable because this is the range of masses where black holes are sensitive to these particles. But we might want to ask, where does that approximation break down? And are there any other effects coming in from the fact that you have these interactions? And indeed, there are important effects that come in. Basically, if you don't have interactions, so this is a similar plot from what I was showing before. So this is the number of particles as a function of time. And you have superradiant growth, where the black hole spins down and sources this blue state here, which is a 211 in the hydrogen language level. And in the absence of self-interactions, this would continue to grow until you extract order 1 of the black hole's angular momentum. However, if you do have self-interactions, in particular for axions, the leading one is a quartic coupling, you can have these different types of effects that arise. And in this cartoon picture, I'm labeling 211 as the blue state, and 322, which is a higher level angular momentum state, as the red level. So once you start building up a population of these axions in the blue state, if you have a quartic coupling, you can have two axions from a blue state transition to a red state with higher angular momentum. And then by conservation of angular momentum and energy, there's an axion that falls back into the black hole. Classically, you can just think of it as a extra source in the evolution of the axion wave equation. And so in the presence of self-interactions, having this 2-1-1 state, which goes much faster because it's closer to the black hole and can extract its angular momentum more quickly, you can cause the next level to grow much more quickly than would happen in a gravitational system, in a purely gravitational system. However, once you have both of the levels occupied, you can reach something like a quasi-equilibrium, where basically the black hole populates the blue state populates a red state, and then there's an energy exchange between the two levels, where you reach this long plateau as the levels co-evolve. The black hole is spinning down and sourcing axions, and the axions are emitting waves out to infinity. This is both good and bad. First, it's bad because you don't have as large of a population of axions around the black hole, so you don't source as many gravitational waves. But it's also interesting because now, as I mentioned, you're sourcing axion waves to infinity. So I didn't explain this here, sorry. So once you have these two states that are populated, which is actually a very precise description of what happens, you can show that at least for a range of parameters, this is a closed system and you don't continue to build up higher levels. Then if you start populating this higher angular momentum state, then again, by conservation of energy and angular momentum, you can emit unbound axions that escape away from the black hole. So here, some of the axions are going back to the black hole and some of them are being emitted out to infinity. Just as in the case of gravitation, the gravitational waves, the axion waves are very coherent and very monochromatic. And in this case, they last a very long time, basically as long as the age of the universe. And so one can ask the question, can we detect these types of waves? Well, it's hard, but people are already trying to do similar things. So I think this is an interesting signal that's worth thinking about. So again, the idea is that the black hole energy through the cloud is being constantly processed and converted to axion waves. So the local theta close to the black hole, the axion amplitude, is small and constant for a very long time. And the velocity of these axions is about this alpha parameter over 6, which can be between 0.1 and 10 to the minus 2. If you think about dark matter, it also is a set of axion waves. If you think of axion dark matter, which is an important target for many experimental searches, then it's also a set of axion waves which are with a much larger amplitude because it's a much larger energy density, a bit of a smaller velocity because dark matter in our galaxy has velocity of 10 to the minus. But you can use similar experiments like this one called Casper that was proposed by someone in the audience to try to look for these types of signals by coupling these axion waves to the spins of nuclei in a large sample, and then measuring the generated magnetic field due to the precession of spins about the axion field. So here you can see that with the types of setups that would be required to detect axion dark matter, you could potentially also see signals from some local black holes. So on the x-axis, I'm showing the axion mass in electron volts, and on the y-axis, I'm showing the effective magnetic field that's generated locally in the lab due to these axion waves coming from these different black holes that I've plotted here. So, for example, Cygnus X1 is a very highly rotating black hole that's a few kiloparsecs away and would lead to a signal that's equivalent to about 10 to the minus 23 Tesla in the laboratory. That's a very small signal, but potentially you could detect it with some futuristic experiments. If you have black holes that we haven't seen before, but are just floating around in our galaxy, which should be the majority of the black holes that are in our galaxy, then you will also see, then you can expect louder signals and can see it with relatively reasonable volumes of these dark matter experiments. So this is interesting because it's a very complementary search in this mass range. So if the axion is the dark matter, typically you would expect it to have fairly low self-interactions because in this mass range it has a very large symmetry breaking scale. But if the symmetry scale is a bit lower, which enhances its self-interactions, then it's harder for this particle to be the dark matter, but it could form these bound states around gravitational waves, around black holes, and emit axion waves that you can then detect. So potentially you could cover most of the parameter space in this mass range, looking for these types of signals. Okay. Any questions on that? In the last few minutes, I want to tell you about another type of signature that can arise from a different type of particle, which I think is can be very dramatic. So switching gears a little bit, I've been telling you a lot about axions, but in principle, this process qualitatively does not depend on the spin of the particle as long as it's a boson. So the process can also happen for a massive spin 1 particle, and we've worked out how it depends in detail. A lot of the rates and the detailed properties are different, but the overall picture I gave you at the beginning, where the level grows and then decays away to gravitational wave radiation, is exactly the same. But if you have these new very light particles that are spin 1 rather than spin 0, so these are particles like a dark photon, then you can have qualitatively different signatures in addition to the gravitational signatures. So there's recent work that was led by Niels and Christina to think about how dark photons, which interact with a standard model, will behave in realistic astrophysical environments around rotating black holes. So remember, I told you that bound states of these particles grow exponentially, and then you have very large densities around the black hole that can be as dense as a neutron star. If you take an electric or magnetic field that's as dense as a neutron star, that's a very large electric or magnetic field density that is can start to Schwinger pair produce electrons if that field couples to our electrons, to standard model electrons. But of course, our photon doesn't have a mass, and so this is some dark photon that has some small coupling parameterized by epsilon that will generically be produced by quantum effects. If you have this field, it will at some level interact with our charged matter, but that coupling will be a bit smaller. And so as this level grows, what happens is that this is still a very large background electric field, which can accelerate electrons and positrons, or it can accelerate electrons in its vicinity, which will generically be there in our galaxy or in the universe. There is a dilute plasma all the time, charged particles. As these electrons accelerate, they will scatter off, they will bend in this rotating electromagnetic field, and they will also scatter off of the strong electromagnetic field in a process that's assisted Schwinger pair production. So basically, instead of producing electrons and positrons from a very large electromagnetic field. There are already photons present from synchrotron radiation that then interact with a very large background field and give it a bit more energy, and then you can cascade and produce many, many charged particles. So this superradiance cloud of photons will generate a very large plasma of electrons and positrons in its vicinity to try to cancel this background dark electromagnetic field. And this looks a little bit like a pulsar. It's not really like a pulsar because a pulsar is a magnetically dominated system where you have a very large background magnetic field that's created by the physics of the neutron star. And there you can also have complex dynamics of charged matter around it that generates high energy photons as well as low energy electromagnetic pulses. Here we started with an electrically dominated system. That's because these bound states are non-relativistic. The amount of energy in the electric component of the field is larger by a factor of 1 over the velocity compared to the magnetic. So it becomes very hard to completely screen these fields. But you can use similar techniques as people use to understand real pulsars to try to understand this weird black hole pulsar. So this is some large electromagnetic field that's rotating. And you can try to understand their underlying processes. So it turns out the underlying processes become quite complex, and it seems like the magnetic fields and the plasma in the black hole vicinity, in the presence of this rotating field and the underlying plasma, causes a turbulent cascade in the magnetic fields around the black hole, which is pretty cool because that leads to a lot of energy dissipation at a range of scales. So Nils used techniques that are similar to what people use for these pulsar systems to understand how much energy is being converted from these superradiant clouds into electromagnetic fields. And as a this alpha parameter, which you should think of as the mass of the new particle, the luminosity can be really large. So here I've taken this new physics parameter epsilon, which tells you how much weaker the coupling is of the dark photon relative to electromagnetism to be at the current bound in this parameter space. And you can see that the orange, which is the full luminosity of the system, can be as high as the supernova luminosity. For reference, if you're comparing to regular pulsars, one of the brightest pulsars, the Crab pulsar, luminosity is down here. So of course, if the system existed and was really at this full brightness, we would have seen it by now. And we think that you can do searches for both in the electromagnetic spectrum as well as correlated with gravitational wave searches to try to look for particles in this parameter space. So for example, if you have a new black hole that's formed, these clouds will grow and emit both gravitational waves as well as in the presence of this kinetic mixing parameter epsilon, as well as this electromagnetic radiation. And you can look for correlated signals in gravitational waves and in electromagnetic waves. Also, if some of the pulsars that we already see today, we don't know for sure because these systems are complicated and we don't understand the fundamental ways that pulsars pulse even for regular neutron stars. But it could be that some of the pulsars we see today are secretly these types of black hole cloud systems. And so you can try to follow up pulsars that you might not have wanted to follow up before with gravitational waves because they don't have the right property to produce loud gravitational wave signals, but they could have the right properties to be these types of black holes. Yes, question. Great question. So we don't know for sure whether they pulsate or not. They have a very regular. So we see in the simulations that there is a periodicity to the emission of the signal, and there is a very strong directionality to the field because the electric field is pointing. The bound states are such that the electric field is rotating at this frequency that's set by the boson mass. Similarly to how we talked about there's a rotation of the scalar states. In this case, there's also a rotation of the vector states, and it's exactly the electric field rotating around. And so you expect that there to be acceleration of particles in some direction, and there should be some generic periodicity. Whether it's exactly like the periodicity of the pulsars or not is really unclear, and you can't get that from the types of simulations we did because they just tell you about the overall energy density that's being extracted. So we expect there to be some periodicity on the signal, but whether it's like really bright pulses or just a modulation is not known at the moment. Yeah, a good question. Yeah. Also requires further work. So probably hard X-ray or soft gamma ray, just based on analogy to what we know about neutron stars. And also a component of radio due to the synchrotron emission, but we don't know for sure what the overall spectrum is. So in these things, you kind of parameterize it as some fraction of the energy you expect to go into both of those bands, but exactly what the spectrum is, you don't know. Yeah. Good. So that brings me to the end of the talk. So we've talked about rotating black holes and how they can produce these clouds of weakly coupled bosons through superradiance, which is a very generic process that happens for any weakly interacting light boson. If the particles are coupled weakly enough, like the QCD axion, you can look for it using gravitational waves or black hole spin down, which I didn't have time to talk about in more detail. If the particles have interactions, for example, self-interactions for axions or interactions with electrons and charged particles for dark photons, then you can create new dynamics. So you support the gravitational wave signatures, but that's compensated by new signatures that are created either through the emission of axion waves in the case of axion self-interactions, or the creation of multi-messenger signals, electromagnetic multi-messenger signals in the case of spin-1 particles. So thanks for your attention, and thanks for having me, and I'll be happy to take more questions.
Questions from audience?
LISA era, if we were observing gravitational waves from supermassive black holes, would there be an analog for lighter axions, or is it too slow to be astrophysically interesting?
Good. Yes, definitely in the LISA era, you will still see gravitational waves. Those could probe lighter axions that would be sensitive to roughly 10 to the 18 to 10 to minus 18 to 10 to minus 15 electron volts. And all of the signals go through the same way. Everything is just down by a factor of the mass, so everything is parametrically slower. But given that some of these signals can take hours, scaling it down will still give you observable signals. Another interesting thing that can happen in the LISA era is that you can also look at inspiraling stellar mass black holes, which could have clouds around them, and that could give you extra dynamics. For example, you could try to infer the presence of a quadrupole that's distinct from what you expect for a regular black hole, or you could cause the disruption of the cloud at some point through the orbit, because it's going to get tidally disrupted if the two black holes come too close together. And you could also cause level transitions in the cloud due to the periodic motion of the potential. You could have extra dynamics that happen there. So basically, all of the signals here translate, but there'll also be extra things you can look for. Yeah.
Yeah, I wanted to ask if I was understanding correctly that the axion field around the black hole will be most, it'll be most efficient at producing this emission at early times after the black hole creation, or is this a long-lived phenomenon?
Yes, so it does. So the signal scales roughly as 1 over time. So right after the creation of the black hole, the signal is maximum, and then it slowly decays because basically, as the system is emitting gravitational waves, the the energy of the cloud is being converted to the gravitational waves. So the cloud will deplete over time, and then as it's depleting, it creates a smaller signal. So good. Yes, it does get regenerated, but it can't get regenerated. The same level can't get regenerated because the black hole already spun down. So the black hole spins down. You form a given cloud of a given angular momentum state. That level radiates away, and then the next level can grow. So, for example, you have the first level. This has the fastest one has angular momentum 1. Then you can have a next level that goes. At this point, the black hole. This level will fall into the black hole because the growth of this causes it to spin down past the superradiance point of this level, and then a second level will grow. Here, gravitational waves are being emitted. However, even though the same amount of energy is going into this state and this state, because of this fact that I described before, which is that this state has higher, so there's a dependence on the angular level in the power of the gravitational waves that happens here, because there's an extra suppression to emit quadrupole gravitational wave radiation, which is relativistic from a non-relativistic source. So the higher the angular momentum, the more dilute and further away from the black hole the cloud is, and the lower the overall power that you emit is. So it's true that eventually the black hole keeps spinning down and keeps radiating gravitational waves, but typically if you plug in the numbers for concrete searches, after you finish with the first level, the power that's emitted will be difficult to detect.
Yeah.
Thank you. Very interesting. I just have maybe a very naive question. For the second part, you talk about a dark photon,
Yeah.
massive dark photon. I'm just wondering, suppose I apply that system to Z boson plus neutrino. Is that exponentially suppressed or that's parallel suppressed?
So there's a couple of issues with applying it to a Z boson. First, because the Z boson is very heavy, it will be exponentially suppressed. The superradiance rates get exponentially smaller as you go to higher and higher masses, if you want to still satisfy the superradiance condition. So that's one thing. If you have like really little tiny black holes radiate principal Z bosons, actually one of the first papers by Detweiler had the comment that you could, if you had really tiny black holes, it could superradiate pions. Of course, that's actually wrong for several reasons. One, pions are not stable, as is the Z boson. So in the time that these things grow, they will decay much faster than the superradiance growth time. The superradiance growth time is it's astrophysically relatively fast, but on the particle physics timescales, it's quite slow. The other thing is the self-interaction. So Z bosons and pions all have quite strong interactions. I've told you that even axions, whose interactions in terms of the quartic, if you convert it to like a dimensionless number lambda, those self-interactions are like 10 to the minus 77. So, and they can have an effect on the dynamics. So if you have particles that have, standard model type interactions, then these clouds will never get to grow because those will dominate the dynamics rather than the gravity. Yeah.
More questions? So here I have one question. Yeah. So to my understanding, so here you mainly focus on the isolated black holes. So my question is, if the black hole has a companion nearby, and how will the superradiance be influenced?
Yeah, that's a great question. So the simplest way to think about it is, again, going back to the quantum mechanics picture. Of course, we're solving classical equations here, but it's the same equations that you'd solve for a hydrogen atom. So if you look at the non-relativistic field for the axion, it's living in some states around a spherically symmetric 1/r potential with some corrections due to the black hole spin. And then if you introduce a companion, that creates a perturbation to that potential. If that companion is far enough away, you can expand that perturbation and see what happens. So first order, you're breaking rotational symmetry of the problem. And so now you can mix states with different angular momentum, which you couldn't mix before. So for example, if you had a state with angular momentum 1, which is superradiating, now if you introduce a companion, that can cause mixing between superradiating levels with one angular momentum and non-superradiating levels with a different angular momentum. So if the companion is too big and too close, it can shut down superradiance. If you plug in the numbers for basically any system, this is quite irrelevant unless the cloud is very dilute. So if this alpha is very small, so if it's very puffy, and the companion is very close, it's not a big effect. But as I mentioned earlier, if you do have binary in spirals, eventually this effect will become important and can cause level transitions in the cloud, which then shut down superradiance or can give you additional signals. Yeah, I can tell you a lot more, but that's the quick answer.
Okay, thank you.
Yeah.
If there is no more questions, let's stop here and let's thank our speaker again.